Okay, we are recording. I hope your weekend was good. So, quick feedback on the homework. You survived it. I asked some people already. Reading the papers was doable. Again, if some of it flies about above your head, that's how research papers are. So typically, you cannot comprehend everything and anything, especially if you're not a practitioner in the field. But the point of giving you some of the papers is just to give you a review. And if you need it, you can come back to it later. So in that sense, that part should be helpful. So we're going to today finish the filtering exercise, and then we will move on to segmentation, which is one of the key exercises in image analysis. So a lot of what follows is under more sophisticated methods. Basically take it like it's going to be fast kind of review of different things that are out there. I want you just to have them in mind if you need them. That's something that is possible, but we will not go into a lot of details because a lot of these topics are interesting, but they're also very specialized, or they might depend on your specific application. So first thing before moving anywhere, there's various filters that you will always try. I mentioned medium filter as one of the easiest filter to apply. So that one is kind of, you will go around the image and you will pick a size of the neighborhood you will look at. So we commented on those circular masks that you're going to look. How big of a neighborhood you should use, it's up to you. The bigger the neighborhood, more information you will lose. You will kind of smooth out the image. At the same time, the size of the neighborhood should not be bigger than the smallest feature you're looking at in your image. So you should have that in mind. So tread lightly and decide that you try to evaluate what are you losing and whether you're losing what you need to lose. Because denoising is information loss. You're going to lose some noise, right? But you're hoping not to remove actual features of your image or create some new ones in the process. So always remember, no matter what you do, and you will go out and try probably a number of different filters, two things. One, try out a number of them, and every time compare both how the image looks before and after, what appears to you that has happened in the image. Pick a number of features in the image that are of your interest. So they might be some sort of cracks or some sort of bubbles in there, or whatever it is that you're looking at. And just try to look at the different sizes of those and see how has this filtering affected those features. And ritually, before looking at the image, write down 3 or 4 things that you're actually interested in analyzing in that image. Okay? And then find a number of examples before even any filtering of those in your image. Say, okay, in this slice I'm going to look at this, this, and this. And then go through filtering exercises, try a number of filters or sizes of masks and so forth, and figure out what is happening to those features. So that's basically, it's something that is of a practice handbook, how you approach these. And also look at the cumulative effect that this exercise has on your histogram. So in this particular case, obviously I lost some information. My histogram looks better delineated, so I have now 2 much clearer and narrower peaks. Okay? And that's good for segmentation. That's what I'm going for. And hopefully I didn't remove a lot of information that I need to get this. So that's something that you evaluate by looking at the image actually and the number of features that you're interested in. So those are like your steps in the procedure. So you will always lose some information. Now let's move on to some of the advanced bits that are all related to filtering in some way or the other. Okay? So registration is a common problem where I have a number of instances, for instance, in time of the same object, and I would like to register them one by one. Okay? For instance, even if I just I go in and I go in for a scan, and I step in this way. Okay? And then at a different time, I go in and I step in this way. Obviously, I'm rotated at 90 degrees to the original. It's still me. But if I'm trying to measure from the image the change between these two time points, maybe something happened in time that I'm trying to track, I need to register one for one, where is my nose in this image, and where is my nose in this image, right? And align them back to each other. Okay? Now that's a fun way to put it. There are no noses in porous media, but there is actually something. So you will typically take a recognizable feature in the image and check that you have, if you have two instances in time that you're trying to align, you're going to look for the nose or whatever it is, a specific feature in your image that you're going to check your alignment. Now, if it's this simple rotation, okay, those things are relatively easy to check for. Okay? So you can basically take two images and rotate one around the other and look at the overlap between the images or correlation of some sort. Okay? And you have, if it's physical translation or rotation, those are simple equations to put together and test. There's quite a bit of testing, and you still have to decide, are you going to do that on the entire image or some subsections? So there might be computationally involving, but it's relatively simple. So rigid rotations are simple. Non-rigid registration gets a little more tricky. And there's an entire field called digital volume correlation. It's used a lot in geotechnical engineering, especially when you're trying to image stress and strain of some testing. So you image something stretching, and then at the next point, hopefully, stress and strain, if you're in linear regime, you didn't go far between 2 points that you're imaging, so you're relatively close, and by computing correlation between the two images, one can figure out what is the actual displacement between the 2 points. And it might be nonlinear in the sense that in one part of the image it's this much, and in the other part of the image it's this much. Okay? That's what the nonlinearity comes in. Whereas when you translate the entire body. Okay? So for that you need some sort of more statistical techniques that we're not going to cover.
What if you scanned two things but you reconstructed it with, say, a different software? Would you have trouble putting those together?
Possibly, yes. But it's still the same. So question is, was it in the same spot? So here's what happened in my PhD. So basically, you had to sample that you're imaging. It was a Berea sandstone, right? So Berea sandstone in itself did not change in the process. But I know to image it, to get the three-dimensional image, I have to rotate the sample 180 degrees. How precise is this software that is rotating it back to the very same position? Initially it wasn't, so it took actually a little bit of work to get it precise, because it has to be precise if I'm imaging at 5 micron. It has to be precise at less than 1/10 of that in order not to notice in the image. If it's like even a fraction of 1/5, you will actually be able to see the shift, and that will affect your segmentation and anything that comes into play. Or yes, it could be done at slightly different. The reconstruction could be done at using slightly different software and parameters. So it could be slightly different energy and so forth. Second problem is that was actually imaging of. So I keep adding fluids to it, and some of them are tagged, and that can actually shift your spectrum and affect what is the actual absolute value of, for solid space, what is the grayscale value that gets assigned to solid spaces in one image versus the other. The fact that I have different range in the second image actually affects that. So yes, but as long as I know that they're physically in the same location, what we will go is we'll do the segmentation first before actually figuring out any kind of registration. So separately segment them, then you know that you're dealing with the same type of numbers. But we'll do segmentation as the next step. So second problem that I actually had that took me, well, I graduated and then I figured out what happened. So I had a polyethylene sample, and polyethylene sample soaked up some oil. So there was and essentially all I could see is that I attempted to register, and I did a lot of manual work. I selected sections. I had 14 different instances of fractional flow. And I would rotate them, and I did all of the possible rigid rotations of each other. The person doing the experiment was swearing to me that yes, he rotated it back precisely, and this machine is very precise, and no, nothing, no shift has happened. Though during the injection, there could be a push that kind of moves the core a little. Okay? So I thought that was the problem. But then I would go and do different sections, and I could not find a linear or this rigid transformation that would, even if you push the core, that would be still a rigid transformation between one point and the other. And I realized later that it's actually that some of the solid space has swollen up and unevenly throughout the core. But what I did at that time is that the problem was happening around near the boundaries of the image. Okay? And I was simply moved all of my analysis of everything that has happened in the pore space was sort of in a reduced pore space, like innermost pore space. So whatever saturations I was reporting and whatever, I was reporting them away from that boundary that looked problematic. So it wasn't perfect, but it was. So there's some of this non-rigid registration would have possibly been helpful, but I didn't have in my model a way to account for changing solid space. So that basically point that one would have to repeat the entire experiment, because that's not what we were studying. In any event, second part where if you have, so this is happening in movie industry a lot, the basic message is as follows. If you have information about something that is affecting your shift in the images, you should incorporate that in correction of the images, and then things will be much better. So in this case, for instance, if you have a movie frame, and then the next frame, you know that like it's not changing much. Let's say even if you have a person walking, there's steps in that, so basically between two frames that you're looking at, there's not much of a difference. However, there's both person walking, and possibly there's a camera following that person. Okay? So there's a physical shift in the camera and the person walking, and one has to account for that. So you can basically, if you know how camera is moving, and you know those things are moving on a track for a reason, if you know anything about movie making, there's a camera that like kind of moves on a little device, whatever its name is, okay? So basically, you know that movement, so you can incorporate it in your analysis and basically nullify it. And if you do, so for instance, if you didn't, this would be the difference between the two frames, and if you actually get that compensation in, then the difference will be much smaller and will actually account for the actual movement of the person that happened. So if you have any knowledge of anything external, you have to incorporate it. Now, registering that's movie industry, and sure it's helpful and it's pretty for all the different reasons. Registering in scientific research, of course, has a lot of good applications. Now, in either medical imaging or materials science, you will typically register two images with and without contrast fluids. We inject contrast fluids into patients as well. Well, we don't, but medical doctors do. In our case, it's going to be before and after certain fluids injected or any kind of mechanical or chemical alterations. And you want to measure what the difference is. That's the whole point, right? You want to put a number on it. Okay? So here's an example from that is reactive flow in porous media. These are SP papers if you'd like to follow up to, but this is basically dissolution of a carbonate core after injecting CO2, okay? Or rather CO2-laden fluid. So there's a lot of dissolved CO2 which reacts with the core and dissolves some of it away. So you can actually, if you look at this and this piece missing here, it's gone. Okay? This one, it's disconnected, at least in this slice. Okay? So you would like to put these on top of each other and see what the difference is in the solid phase and where is it? Is it in certain large pores, is in certain small pores, like things like questions like those, right? But that's not, especially since the core is irregular, even though it was cored as a cylinder, there's a lot of these things at the boundaries. It's not necessarily a trivial thing to adjust it forever. And here, basically, you have, they were looking for, they found that there were certain displaced particles, okay? So here, it's not there, here it's not there, here it's there, right? But basically, they figured out whether they're disconnected in the pore space or connected to the main solid phase. So what happens in this solution, if you dissolve this piece over here, and this one disconnects, it's going to start flowing. So whenever you have reactive flow, you might have the reactive part, oh, part of it just dissolved, part of the carbonate is dissolved. And another, there's actually formation damage going on by particles that chip off and move down the core. Okay. So this solution might actually chip off certain particulates and they will start moving through the core. And of course, they're going to affect permeability and so forth. So permeability comes, or is affected both by the dissolution of the space, which could be kind of relatively homogeneous and happening on all surfaces, but also by particulates that get chipped off and start moving downstream, and that can affect your flow as well. Okay. Now, this is when I have two similar type of images that I'm registering, I might have also two different imaging modalities, but they are, or maybe image at two different resolutions, but they're imaging the same thing, and they're still somewhat similar. Right? So there are techniques for doing that. We're not going to do details, but for instance, here there was an example where there was a large core at a relatively coarse resolution, so you can see this image here. And then there's a small core that was cored and imaged at very higher resolution, so you get the level of details like here. And then you would like to find out where is this small core, this small image, where is it in this large image? So since they're not the same images, that's not necessarily an easy overlap. So there are different techniques. One could upscale this one to the resolution of this, or interpolate this to the resolution of this, and try to correlate the two to move one around the other and try to find which correlation is the best. All of those are pretty computationally involved. So it's also best to have some idea, well, where did I core this before you actually, how far did it really go before you actually go and search the entire space. So we're not going to spend too much time, but this is some software that is available out there should you want to try that. There's a paper here that is trying to basically give an algorithm, not trying to, but gives an algorithm for 2D to 3D registration. And there's software options. So the free one is the Insight Toolkit and is optimized for medical imaging processing. So it probably works rather well for porous media as too, but porous media is going to have a larger images that basically have higher computational cost for registration. But it can be parallelized. There is Richard Ketchum's Align 3D. It's in itself free, but the entire software that comes from Richard Ketchum in geology is based on a programming environment called IDL, and that itself is not free. Okay? Then there is Aviso-Fire. That Aviso-Fire has changed names ever since. That software it's now called PGE383, and it's rather costly. I find it typically too expensive to fund it for my own research, and I kind of develop these things anyway, so I don't. And then there's various possibilities in ImageJ and Math. Okay. I haven't really tried Loney, but I had some search when I was looking for these. I found it, so I put it there. Now, basically, another task that is part of this registration is that I might have two different images at two different levels or resolution, and I might interpolate one or the other, to actually match them. So some level of interpolation is required before you can actually apply the algorithm. Okay? Well, interpolation in itself is far from optimal, especially when you have sampling that is, and that's, for instance, medical CT downstairs in David DiCarlo's lab. Typically, you're going to have in X and Y, you're going to have 1 millimeter and 3 millimeters in Z. And we had one such, and this is the image we started off with at the beginning of the course. So basically, we did 2 different types of interpolations. An image J, just to fill it in, to have the same, to have a cubic voxel. Okay? Now, there's filling, and this is also in the movie industry, you're going to fill missing frames. For instance, if for some reason you uploaded your movie to YouTube and the resolution has decreased and some of the frames are missing, you might have to fill them back in, and you might want to use something that is a little more. So in movie processing, this is a common topic. So there's something called optical flow that tries this sort of like a nonlinear adjustment. It basically tries to recognize objects in there and see how they would change from frame to frame without just blindly interpolating. And we know if I just blindly interpolate and I'm crossing the boundaries of phases, I might start blurring too much. Okay? So this is trying to determine what are the gradients in my image, because wherever I have a large gradient, I shouldn't proceed very fast, or I shouldn't interpolate with a large step. So that's optical flow. Now I'm not gonna actually go over this. This is something if you want to work on. I'm just gonna comment that just like in most of numerical methods, you start with Taylor formula and you go from there. So basically, you're trying to estimate nearby location based on some location that you know. And of course, to the first order, this is in 3D, there is a gradient times the actual displacement vector. So if you remember anything from your calculus, Taylor formula should be A. Okay? And then they're trying to find, well, what is the gradient? They're trying to find the velocity, or essentially this displacement part, so that this is very close to 0. So it comes down to solving a set of equations, except that you need some constraints that is coming from the image or analyzing image in itself. So in a nutshell, that's it. So I'm not gonna spend time. But basically, let's look at this image. So if I should have a movie that basically compares. So there's an image filling in the slides in between, and we are supposed to see the difference between optical flow and just linear interpolation. So you can see the jumps in this between the frames that are much kind of choppy. And this one kind of moves smoother through the image. So when I filled in with things that were continuously or changing in a differentiable way. Does everybody see the difference? Yeah? Let's try again. Everybody's like, I don't know what I'm seeing. All I can see is that I see a lot more jumps here. Now, one would actually should do a profile or something function through one of these areas to actually all right. I'll let you be the judge. Another method, and this is also just a general comment, is there is filtering out noise or local blurring that we have, and just like median filter will do the job for that. The second problem that we might have is that if you remember, there's uneven grayscale values in the same image. So let's say that I have a light microscopy image. I might have in top portion a little more illumination and in the lower portion, not so much. So then suddenly I will have different grayscale values in the top portion of the image and then I have in the bottom. And I might be actually looking at something that I can clearly recognize. Let's say that it's microscopy and it's some cells, okay? And I can clearly see the cells, but if I want to recognize them by grayscale value, what I have as grayscale values at the top and the bottom is not the same, but differences or jumps in grayscale values are. Okay? So that requires that I actually go and analyze different regions slightly differently and compare them kind of globally to see what's going on before I decide how to filter and how to adjust. So one of such denoising filters is called non-local means denoising. So basically, you go through the neighborhoods around the image, okay? But before you update each neighborhood, you go to the other neighborhoods that seem similar to this one. So possibly they have the same jump, okay? And then you update according to that and possibly normalize. So in that case, you're hoping to avoid this uneven things. And this is, of course, nice idea, but it sounds like something very slow if I'm moving from something that I'm doing locally to some global comparison before I actually do the change. Okay? So that could be involved. And there are papers on that, but non-local means denoising is available in ImageJ. Just follow this plugin. So for instance, here I can see, it's a little harder to see, but basically here, I obviously see this is a grain. And this is a grain too, but it seems that shades here, the gray, are overall shifted. So if I want to account for that, I might want to go with non-local beads. Okay. There's also wavelet methods, and this is something that is very common in signal processing. We know from Fourier transform that if I split my signal into a bunch of signs with parameters or signs are my basis functions, and I look at the multipliers for each basis function. Okay. I can decompose these things and then work in this Fourier transform space. Now, wavelets will do similar. It's just that the set of basis functions will actually be tailored a little more specifically and not necessarily just signs. Now, once I actually go, and there are different wavelet bases that are out there, if you now move to this wavelet space or Fourier transform space, however you want to look at it, it's kind of easy to distinguish the structure and see which modes are dominant modes, and those are typically the ones that you take, and you remove the rest as noise. That, however, is complex to implement in image processing because signal is not one value over time. I actually have an entire image. Okay. And how do I look at it in time? Do I go as one of these z directions as time? And how do I look at it? It becomes a little more complex, or possibly I have it in time, but it's now this three-dimensional structure. So suddenly the problem is much more computationally difficult. That said, with the computational resources moving within 10 years, it's not going to be a problem, so you can look out for wavelet methods. Okay, I'm going to skip this one. And then I'm going to address, there was actually a question about sharpening, and you can often sharpen the noise. So essentially, whenever I have image, what we know that we will have some, even if I had a very sharp edge, okay, once it's imaged, there will be some smoothing around it. And that smoothing can be looked at as convolution with this blurring function. That function is often called point spread function. Okay? Now, this is combination of hardware and reconstruction issues that result in this point spread. Now, this convolution is basically multiplication in the space of Fourier functions. So if I know what was my blurring function to begin with, I could try to reverse the process. Okay? So that works only if you actually know what your blurring function was. So if you figure out the knowledge how to do that, then actually you can go and remove that blur because you knew what kind of caused it. Okay? You're looking at the result of it, and you know that some original image convolved with this blurring function is your result. Okay? And now you're saying, well, if I know this function, I can try to retrieve the original image. And that can work well if you actually know that. So here's an example. This is an example with the image at insufficient resolution. And with a little bit of sharpening, this is what I get. Okay? Now, this is something that it's kind of a little bit strange because it's not necessarily straightforward operation. So there is a little bit of optimization and guessing at what this original could have been. Okay? But it works kind of only if you actually know that you had blurring to begin with. Otherwise, you're sharpening, or this is my twice the resolution of the same image. So this is the original, this is sharpened. I still can't necessarily get what there was when I had better resolution. So it's always better to try to image a better resolution if you can. Now, in this particular example, and this is the one that we worked with, this was actually fairly sharp in its own, and there was not that much blurring near the boundary. Okay? So since the noise that I see is not the result of blurring, once you try to sharpen, this is not it. Okay? So you have to know, again, if you're trying to apply it, you have to know that some blurring has happened before you sharpen. So in this case, this did not help because there was no actual blurring. Edge detection is something that is, so let's actually do this example to wake up a little from all of my talking. So this is the example that we shared in filtering exercise. So let's do the open up. Fiji. Open, so I think it was the loss, no, there we go, this one. Do another copy of this just to have it. So if I would like to identify where edges are, sometimes edges are of importance and outlines. So I can go to Process, Find Edges, and see them. So you can see very much, so what does this mean? For edges, I have very large values, these white values, 255 or so, near where I had boundaries. So any kind of jumps in original grayscale values, so here I have a jump, for instance, from 126 to 41. Okay? So I will find very large edge just near this boundary. Okay? So it's really a gradient. Okay? Whereas around here, I have relatively small values, though there's quite a bit of noise. So they're detected as small edges. Okay, so noise affects efficient finding of the edges. Okay, but it gives me some information, and one can actually say, okay, well, if you have these large gradients can still be found, and we're going to go to the segmentation next, so we can try to isolate them. Okay. And that will actually give me information of where the possible shape outlines are for this grain. And it might be actually the whole point. Let's say that I'm looking at the image of cells, biology samples, foam, or something like that. Edge is what I'm looking for, right? I'm looking for bubbles or something in my image. So one problem, again, is that I do have to do some filtering to remove these small edges. So there is no way around filtering. I do have to deal with some filtering, but I can use, so whatever you do, recall that you have two basic information in an image: actual image values and image gradient. No need to go to higher order or anything. Okay. So essentially, image gradient is essentially this picture of edges is picture of image gradients and jumps around the image. Okay. And in itself could be a task to find edges. Okay. So I might, whatever algorithms I have, I might adjust them to function. For instance, if there's some front that is moving, it might change its speed of movement based on the local gradient in values. Okay. There's also texture, so you can simply look at the variance in 3D. Okay. And this is something that you can look at again to assist. It's really just for every neighborhood, what is for my pixel the variance from the statistically the variance in that neighborhood. Okay, so every statistics on a neighborhood has mean and variance, and I can look at the mean, and my mean filter will actually replace with the mean or median in that neighborhood. So that filtered image is actually image of means or medians. Okay, but I might want to look at the variance basically to see what the differences were in different neighborhoods. And again, I'm going to have larger variances in those cells that actually had edge between two phases within them. Okay, so those are going to be high variance regions. Right. So that's essentially it for filtering. You're going to get a homework example to basically a homework based on filtering, which is going to be a practical one. If you really, really want, I do have a wonderful paper that you could read as well. Let me know. I can actually just suggest it's actually a review paper on filtering methods. So I'm going to probably just add it to the slides for your information. But overall, I think practical homework is now, in order to offset all of the reading of the papers, is going to be really an ImageJ exercise. And it's actually going to show in some extent how in different sizes of features that you're looking for in the image are disproportionately affected by noise. Okay? So if I want to recover the original features, I might need to take that into account. Okay? All right. So I think that's, I can introduce segmentation, so I have less to introduce next time. Yeah, I have about 5 minutes. So segmentation, again, is one of the main topics that we're going to cover, and it's a starting point for anything else that is coming after. A lot of the filtering will actually come into focus as we try to segment, because we are actually filtering our image so that we can segment the image. Now, what is the segmentation? So here, if I look at this image, this was imaged by Dorothy Wildershield, and I have glass beads, I have air, and I have water. Okay? And my eyes, obviously, so this is a three-dimensional image, and I'm looking at 3 orthogonal slices. You can get this in MATLAB by slice function, and there are some ImageJ versions that we're going to work through later to get this type of imaging. So now I would like to basically have an image that is going to be an image of labels. This is going to be air label, solid label, and water label. Okay? Because I might want to quantify saturation, right? And I need that labeling for finding saturation. So this process of separating voxels or pixels into a smaller number of distinct groups, and what type of groups and how many of them depends on the image and what have we imaged, is called segmentation. And the whole objective is to simplify this representation into something that is more meaningful, and also locate certain objects and quantify them. So, for instance, you might want to look at the residual saturations and look at the disconnected blobs of one fluid or the other, because that's, of course, important for your residual saturation. Or you're actually looking at the image of the solids and you want to identify individual grains. So spheres are relatively easy to identify, but some sort of a sandstone or something more complex could have grains that are not so easy to identify, and you want to actually simply do statistics on those grains. So technically it should be easy. Our eyes see the differences, so then let's just go and do it. Now, this is a crucial step, and I will repeat that over and over, because everything else that you do typically, whatever other modeling, and digital rock petrophysics basically refers to the fact that I'm taking images and then I'm running some models based on those images and producing some newly derived petrophysical properties. Maybe it's permeability, maybe it's something more than that. Okay? So everything else afterwards depends on how you do segmentation. However, at the same time, in papers in general, because it's kind of a menial or boring step, it's underreported how it's done. So there are choices that everybody makes as during segmentation process that are sometimes reported really well, sometimes not. And my preference is to report it and put it in appendix, because often it doesn't bring much to the story. I get that. It's not the scientific story in itself does not depend on how you did the segmentation. Hopefully you did it right, and after that it doesn't matter, right? So, but for everybody's sake, put that information in some sort of appendix, at least in your thesis or in the paper, or document it somewhere, okay? So, related problem of segmentation is actually the one of edge detection, and here's a much prettier example of multiple edges. So, of course, if I have hair here, and this was working on a colored image, so obviously this green background is ignored, okay? Because the object was the person here that was identified, so these edges can create an artistic rendering. You can take your own photograph, turn it in black and white, or even you don't have to, and work in ImageJ with edge detection to have some fun. Okay? This could be your new Facebook photo. In any event, that could be actually a homework exercise. So, anyway. Or it could be just the actual object recognition. So this is actually a test. How many of you see a dog in here? You know Dalmatian dogs? There's a dog drinking in the creek or something. Drinking, I'm imagining drinking. Maybe he's just sniffing.
Yeah, okay.
Right? But his hind legs are gone. They're basically in the background. Does everybody see a shape of a dog? Here's a head. Here's a dog. Here's a leg. And this leg is kind of missing, or at least I can't trace it. Huh? So human eye, or some human eyes, can actually detect an image, but training a computer to do so in this particular image is called good luck. Okay? So object recognition and edge detection are related to segmentation, but is often done on photographs, and we're not going to necessarily go into details of those. So with that said, I see you next time.
Your shoulder, the computer picked out really well, has lots of edges, even though my eye barely notices edges on your shoulder. But the bush, which the human eye sees really clearly.
And I think that's because the system said this is color image, so it said ignore green.
Oh, no, but it's got the green in the flower. It's got the green in the flower.
Yeah,
I
but
think it's
that's
just a contrast. Whereas there it's going white to black.
you say that this contrast
Yeah.
is smaller than this.
Yeah. Maybe.
I wouldn't say so.
White to black or green to black less so.
Well, take this image from the PDF that I posted and play it in image where the contrast, because this is red, green, and blue, right? So you need to take the red, green, and blue channels and see where the contrast is.
Yeah.
I guess that makes sense. What? What's your question?